Hello, everybody, and welcome back to Geography 340 Climatology. I am Dr. Zach Hilgendorf, and today our lecture topic is going to focus on solar radiation. So here's our sun, this big bright ball of star and gas that gives us energy. And the surface of the sun is roughly around 5,500 degrees Celsius. So we're curious about things like what is the electromagnetic emission rate from the sun's surface in watts per meter squared? What is the wavelength of max electromagnetic emission from the sun's surface in micrometers? We've talked about these in kind of our energy lecture in the previous one. Sun's surface, or the surface of our Earth, is only about 15 degrees Celsius on average. So here, questions like what is the electromagnetic emission rate from Earth's surface in watts per meter squared? What is the wavelength of max electromagnetic radiation emission from Earth's surface come up? And we kind of can look at it in using a couple of different graphs here. So here is the electromagnetic radiation emissions curve for the sun. We see three different kind of designators here that we've called out: ultraviolet and shorter wavelengths, the visible light spectrum, and near infrared and longer wavelengths. So here we can see that about 6.7% of the electromagnetic radiation from the Earth, for the sun or from the sun, is the ultraviolet and shorter lengths. Well, 46.8% is from the visible light spectrum, and 46.5% comes from the near infrared and longer wavelengths. But what does that look like for Earth? Looks like this. And notice that there are some longer wavelengths here. So it is 100% thermal infrared is what the Earth emits as electromagnetic radiation, or nearly at least. So the Earth emits what we call long wave radiation. The sun emits short wave radiation. Again, we touched on this previously, but these are the dominant modes of energy emittance from the sun and the Earth as bodies. So here we can see again our sun. So radiant energy emitted by the sun's surface is about 6.3 times 10 to the 7th watts per meter squared. So our total solar electromagnetic radiation emitted by the sun is on average 3.83 times 10 to the 26th watts. And then we look at, that energy emittance and how it diffuses through time and space. So if we were to extend even further to a different orbital body, like our Earth, some 150 million kilometers away, we ask ourselves here, what is the intensity of solar electromagnetic radiation in watts per meter squared at this distance for which an object can use, like our Earth? And it's about 1,361 watts per meter squared. And we call this the solar constant. So this is the average annual solar radiation arriving at the top of our atmosphere. In a little bit, we'll touch on what happens to the energy as it encounters obstacles within our atmosphere, but make sure to note that this solar constant represents the power per unit area of solar irradiance across the surface of our planet. So let's talk a little bit about insolation, and that's where we're going to spend the bulk of the rest of the lecture here. So only about 2 times 10 to the negative ninth of all electromagnetic radiation emitted by the sun strikes the top of the atmosphere. That is a incredibly small percent of energy emitted by the sun hitting our Earth. It's still a lot of energy though, because it's about 1.74 times 10 to the 17th joules per second, or watts, which comes to be about 5.52 times 10 to the 24th joules per year. Now, humans produce and use about 3.93 times 10 to the 20th joules per year. So in less than an hour, more solar energy strikes the top of our atmosphere than humans use and produce in an entire year of our existence. So let's look at this point here, this basically flat plane against the side of our planet, top of our atmosphere, that's where we see that 1,361 watts per meter squared. Now, the sun's rays we think of as parallel rays of solar electromagnetic radiation. So wherever you are on the planet, the rays are coming in parallel to one another, not parallel to the surface of the planet or perpendicular to the surface of the planet. So they're coming in at different angles depending on where you are on Earth's surface. If you're on the shaded side of Earth's surface, you're not really getting any of it. There's obviously thermal exchange that happens between the cooler and warmer parts of our planet, but if we think of it here, this half sphere of Earth is what's receiving Earth's rays during the day. So we want to ask, like, how much solar electromagnetic energy does Earth intercept in watts? And what's the total amount of insolation? So that ends up being about 1.74 times 10 to the 17th watts, or roughly 341 watts per meter squared. So spread out across every inch of our planet. So to really understand how to calculate and quantify insolation and how it's spread across our planet, let's pretend that we are a person on our planet. So this is what we call the subsolar point in this case. Subsolar point on a planet is the point at which the sun is perceived to be directly overhead. And that's really important for insolation because we want to calculate insolation intensity. We have to think about where our sun is relative to where we are on the planet. So here's the equation for insolation intensity. It is SC, which is our solar constant, that 1,361 watts per meter squared, times the cosine of the zenith angle, which is the latitudinal distance from the subsolar point. So Earth is perceived to be directly overhead, 90 degrees overhead at the equator, right? Makes sense. It's our 0-degree latitude. But you have to do that relative to the subsolar point. So you have to look at where you are vertically, or looking at it from a latitudinal perspective on the planet compared to that subsolar point. So are you 15 degrees? Are you 30 degrees? We're going to look at a lot of those in the next few slides to kind of get an idea of how that insolation changes. And then you could also do the solar constant times the sine of the sun angle, which is just the angle of the sun directly overhead. So let's pretend we're a person on the surface of our planet. And we are standing at the equator where the sun is at 90 degrees directly overhead. Our zenith angle is going to be 0 degrees, because we are right on the subsolar point. The sun angle is going to be 90 degrees, because we are right on that subsolar point. To get that sun angle, you just subtract the zenith angle from 90. So 90 degrees minus the zenith angle to get kind of that offset. And then we like to look at this in terms of a 1 meter square. So it's easily quantifiable. So that ends up saying that for any given 1 meter per 1 square meter on our planet, this is how much radiation is coming in. So what's the insolation intensity here at this point? Well, go ahead and you can pause the video here and use that equation we just learned about to figure it out for yourself. But here it's going to be 1,361 watts per meter squared. That's our solar constant. We are directly overhead. That's what we come up with here. Now, let's move out a little bit. So let's say that we are here. There is the radius for Earth. So that's directly from the center to the subsolar point. Here is where we are. That's about 15 degrees. So about a 15-degree offset is our zenith angle. So then what is our sun angle here? We don't know yet. So we can say, 90 minus the zenith angle, that should tell us our sun angle. It ends up being 75 degrees. So then what is our insolation intensity? Go ahead and pause the video here and just try and figure it out on your own. So take that solar constant and then whichever you prefer, the sine or the cosine, and try and figure it out. You get 1,315 watts per meter squared. All right, let's try another one. Here we are a little bit further up our planet. That's a 30-degree zenith angle. So what is our sun angle? Well, here it's easy. It's 60, right? 60 degrees. 90 minus 30 gives us 60. What's our insolation intensity? Go ahead and pause the video here while you're trying to figure that out. You get 1,179 watts per meter squared. All right, let's try another one here. We're much further up. We're about 45 degrees now, right about kind of where we live on our planet. What's our sun angle? Should be easy now, right? 45 degrees. What's our insolation intensity? Go ahead and pause the video and you should be able to figure it out. You get 962 watts per meter squared. Okay, let's move up a little bit further. Here we are up at 60 degrees. So our sun angle is going to be 30 degrees. There you go. Insolation intensity, go ahead and pause the video and try and reason this out. You get 681 watts per meter squared. Okay, let's move up. Got two more here. Here we are at 75 degrees relative to the subsolar point, so way up in the northern portions of the world. Our sun angle, 15 degrees. So notice, and this is a good one to start really noticing this, is look at the dispersion or diffusion, or dispersion of this solar ray on the surface. That 1 meter squared section is getting less energy because that band is at such a low angle and it's so spread out over the surface instead of being concentrated on the surface. And this is a really good part of the visual to kind of see that. So go ahead and figure out the insolation intensity here. Go ahead and pause. You get 352 watts per meter squared. Okay, now this next one, don't let it trick you. Here we are at the in the poles at 90 degrees relative to our subsolar point. What's our sun angle here? 90 minus 90, right? Horizontal or parallel to our surface. 0 degrees is our sun, is our sun angle. So what is the insolation intensity here? Go ahead and pause the video. 0, right? Because it should be obvious you're multiplying that out. So anything multiplied by 0 is 0. So here at our poles, we're not getting much energy, right? We're not warming the surface as much as you would in those lower sun angle, or I guess the higher sun angles, your 90s to 45s or so. And here we can see, just kind of getting an idea of how that changes depending on where you are on the planet. So to summarize, insolation intensity is equal to the solar constant multiplied by the zenith, or the cosine of the zenith angle, or the sine of the sun angle. And here are what we just found, right? This is going from 0 degrees of latitude from the subsolar point all the way to 90, kind of how those insolation intensities change. And this has been pretty well graphed out. And we can see here, So some of you, or all of you, I suppose, who took Geography 104 probably did this in the one of your labs where you're trying to figure out insolation intensity in the seasons, right? So you can see based on where you are on the far left there at the 0 degree zenith angle, so right at the subsolar point, you're at 1,361 watts per meter squared. And then you can see how that decreases depending on how far away you get from the subsolar point, from 0 on your zenith angle. So we're going to end by looking at Earth's energy budget. So if we look at all of the radiation coming to our planet from the sun as 100%, it is impacted by certain things within our atmosphere. So about 6% is just reflected by particles and things in the atmosphere. Another 20% is reflected and never reaches Earth by the clouds. And then another 4% is reflected from Earth's surface. So then we take a step kind of to the right. We see absorption as kind of what is being absorbed into Earth's system. So about 51% is absorbed by land and the oceans. Another 3% is absorbed by the clouds, and another 16% is absorbed by the atmosphere. So what about what's being emitted, what's being lost, in conservation of energy, energy in, energy out? So you've got about 23% is carried to clouds and the atmosphere by latent heat and water vapor. Another 15% is radiation absorbed by the atmosphere. Another 6% is radiated directly to space from the Earth. And then finally, 64% is radiated to space from clouds and from the atmosphere. And to recap, so we've touched on short and long wave radiation briefly in this video. We learned what the subsolar point, the zenith angle, and the sun angle are. And then we learned how to calculate insolation intensity and about Earth's energy balance. So the next ones, we're going to be looking at Earth-Sun geometry and the seasons. So stay tuned and we'll see you in the next video. Thanks.